All right, so today we get to go through week 7, theory video, dealing with photodiodes and current to voltage conversion. So photodiodes are work just like regular diodes. They need a certain amount of voltage, and then once you get above that voltage, it lets the current flow through. The difference between photodiodes and regular diodes is that the photodiode, that voltage or that energy, that power, that initial 6 volts that we usually talk about, that actually comes from light. So the photodiode has a lens or some transparent window, lets light in, and that light going through then excite the electrons in those p-n junctions and make them jump, and then obviously make current flow as they start jumping from the p side to the n side or vice versa. They're used in a lot of things: cameras, Blu-rays, TV remotes. So they're pretty good light sensors. So again, if you have a certain amount of light hitting them, they'll start to let current through. So you can use that as a sensor as to how much light is actually coming in. So I can use in navigation, can use in solar cells for solar power applications, photovoltaics. So again, what we have here, we have some form of light. That light is then going to excite some of these electrons and make them jump from p side to the n side, excess protons into the holes, just like a normal diode. And then we have that current flow, so electrons coming out of that n side into the p side. Obviously, conventional current flow goes the opposite direction. So again, we have light coming in, causing the current to flow, and you need a certain amount of light as a threshold, kind of like that 6-volt threshold. In this case, it's kind of like number of photons. So I need a certain amount of electrons to be excited to go across the gap, and that needs a certain amount of light. So photodiodes have a linear response to light. So in other words, the current that they're letting through is a function of the brightness. So the more light that comes through, the more current they let through. And so that current is proportional to number of photons. So epsilon is the energy per photon, basically depends on the frequency and Planck's constant. N dot is the number of photons per second. And then this fancy R is called the responsivity, usually measured in either amperes per watt or microamps per microwatt. So again, here if I have some light source coming into my photodiode, the photodiode, regular diode symbol with some arrows representing the light hitting it, that's going to create some current based on the intensity of that light, essentially. So photodiodes have IV curves, so current to voltage curves, that look somewhat similar to regular diodes. You have some voltage that you need to surpass to turn that thing on, and once it's turned on, the current goes up pretty fast. There's some reverse current, in this case called dark current, that's fairly negligible. So again, a very small amount of what was called leakage current before, now called dark current for what should be happening with no light going on. So to get these current through, we actually have to hook them up in reverse bias, so actually backwards compared to most diodes. And then as you increase the light level, that increases this reverse current. And so that's where it lets the current through. And individual photodiodes have very small currents in them. But what you do is you string a lot of them together, and that's going to provide you a big photovoltaic cell, essentially. So that's kind of what's used in solar panels. And so again, we usually have these in reverse bias orientation to let through more current. some conventional voltage source to amplify that current output. So generally don't have just a photodiode causing current in your circuit. You generally have a photodiode as well as some form of battery to amplify that amount of current going through there. So photodiodes can be thought of as a current source. They produce a current, but normally when we talk about electronics and electronic circuits, we usually talk about voltage sources. So we have a battery, a DC battery that's a voltage source. We might have some AC voltage source, and it's generally, we think of the current being generated from those voltage sources. In this case, we have a current being produced, and so what we want to do is convert that back into a voltage to kind of make it align with all the other ways, all the other circuit devices we have, batteries, and things of that nature. So the question is, how do we generate voltage from current? So there's a couple ways we can do this. First option is to use a resistor. And so it just has some current coming through here, reverse bias, battery, resistor, current going through there. So slight problem with this is that in the semiconductor, in the photodiode, there's a certain amount of capacitance that's naturally produced in any semiconductor. So based on that, I essentially have a capacitor and a resistor in series. Resistor and capacitor in series, RC circuit has an RC time constant. So I have some time constant tau, which is the resistor that I have in my circuit, and then the capacitance of the diode. And that is essentially linked to response time. And that is a problem because it leads to kind of two opposite things that I want. I generally want to have a high voltage. To have a high voltage, you need a big value of the resistor. A big value resistor makes the time constant really big, but that gives you a really slow response, and that's not what you want. You want a fast response. To get a fast response, you want a small value of the resistor, but then you have a small value of voltage. So what we're trying to do from this current is to get a large voltage out of it, but to do that with a resistor, I need both large and small values at the same time. So that's not great. The second option is to use a transimpedance amplifier. So that generally looks something like this. Variation of an op-amp, so it looks very similar. I have an op-amp here, negative feedback. Then I also have a current source hooked up to that negative feedback input. So for this guy, it's kind of tough to figure out. Usually we want to find what the gain is, gain being the voltage in divided by voltage out. I said that backwards. The gain being the voltage out divided by the voltage in. But in this case, I don't really have a voltage in, I have a current in. But what I can do is take that current and that V out voltage and voltage divided by current gives an impedance just by Ohm's law. V equals IR. So voltage divided by current gives a resistance, which is impedance measured in ohms. So this conversion from current to voltage is going to depend on the value of the resistor. To tell me basically, again, how much that's sort of amplified, or whether I get usable voltage differences from my current source. Analysis of this is very similar to the op-amps. So I have no current into the plus or minus terminal, so no current coming in these two little branches. And then I have negative feedback. So negative feedback means that my V minus and then my V plus want to be the same thing. So V plus connected to ground, that's going to be 0. Which means V minus is going to be 0 as well. We look at Kirchhoff's current law at this node right here. I have IF coming in, I going out. So whatever goes in has to go out. So IF equals I. And then if I look at just at this part of the circuit over here, the voltage across this resistor RF is V out minus V minus essentially, but B minus is 0. So the voltage across RF is just V out. So V out is RF times IF, but IF is I. So V out is just RF times I. So the circuit we just saw was for any current source. Now we want to specifically put a photodiode in there as the current source. And often there's a capacitor added up here for stability. Doesn't really affect the results too much. So we're just going to kind of pretend it's not there, even though usually there is one there. Then I want to look at what actually happens to the circuit. So I have a voltage on the diode. That's a fixed value. This VB voltage of the battery. So the diode looks like I have some effective resistance of this RF resistance divided by the gain of my amplifier. Gain is usually a really big number, so my effective resistance is much smaller than this load resistor RF. Which means my time constant, essentially the value of R that this diode sees, is very small. RF times the capacitance inside that diode as well. And so this is a much smaller time constant than what we saw in the previous version. So I can still use a big value of RF, and that's still going to give me a big value of my V out. So I'm still going to get a pretty big gain here. But I'm also going to have a fairly small response time, because what the diode actually sees is a smaller effective resistance, and so that time constant is small. So again, this is a way we can do it and still have the two things that we want: a large output voltage as well as a fast response. So in lab, I'm not sure how much this was modified from the original in-person lab. So this is taken from the in-person lab. May have something like this in lab this week, or may not. I can't remember exactly what this was modified to. So that was an example of something called an opto-isolator circuit. They're used essentially to isolate two circuits, but still allow them to communicate information. So what we actually had here, you notice there was one circuit here that basically put a function generator into an LED. So this LED essentially blinks at a certain frequency. That blinking at a certain frequency makes the diode produce a current, and that current is also going to be at a certain frequency, which would going through this transimpedance amplifier, using output voltage at a certain frequency, and that output voltage at a certain frequency was used to drive a speaker, and so that speaker would essentially output the sound of that frequency. That's what this part of the lab was supposed to do. I'm not sure if you're doing that or not. But these opto-isolators a lot of times come on one single IC chip. And so a lot of times what you have is a photodiode and a light source included in that. And so you have, again, some sort of source and some sort of sensor. So this source blinks or turns on and off, whatever it does. And then the sensor recognizes that. And so these two circuits, whatever's on the left, whatever's on the right, they communicate in the sense that the source is telling the sensor what to do. And so the circuit on the left is influencing the circuit on the right through that communication. Plus a closed pair example. There's also a few other versions. Slotted coupler with a blocker, so you can actually turn this on or off, whether you want the source and sensor to communicate or not. You also have a reflective pair, so emit a light reflecting off an object into the sensor. There are many different ways to do this. And then last topic this week involves analog integration, also a little bit of analog digital conversion. So if you think of the difference between an analog signal and a digital signal, an analog signal can take whatever value it wants as time goes on. Digital signal is generally either kind of on or off. It's either some value or zero. And so this kind of relates analog and digital to in the integration sense to actual integration and numerical approximations of integration. So if I take this curve here, for example, my analog signal can be any value I want. So this nice smooth curve is kind of my analog signal. I can approximate that by a bunch of different digital signals. So I can take a digital signal and essentially multiply it by some value to kind of take these sample points. And so those are kind of like sample points of my curve, and integration being the area under the curve. These digital sample points give a pretty good approximation to the actual analog integration, just like you've seen in calculus class. And we saw a few weeks ago, we can use op amps to make circuits that integrate these analog signals. And that's going to be a more accurate way to do it rather than in the digital ways. And so we've seen these before, my integrator op amps in week 5, same ones we've seen before. So my output is the negative integral of the input, the way this is laid out. So the in has some positive value, some negative value, some positive value, some negative value, which means that the out has some negative slope, negative slope, positive slope. Integral of a constant is that constant times t, linear function. So that constant gives you the slope of these lines on the v out. And relationship between v out and v in officially, you can see integral of v in, but also with this factor of 1 over rc. So the slope here is that value divided by rc, minus sign since it's inverted. Now what happens if I have some DC component into V in? So instead of having this be some positive value, some negative value, so something like +5, -5, +5, -5, what if this is kind of all offset? So I have kind of 5 volts added to that. That brings me up to +10, 0, +10, 0. Generally, we don't want that. We want everything to be kind of centered around 0. Well, if I'm trying to integrate that, instead of being a nice integration function, a nice sawtooth function, centered around 0, it's going to be some weird sort of, 10 slope, 0 slope, 10 slope, 0 slope. And so that's going to be kind of a weird signal that's eventually going to go to infinity, and that really can't happen because I only have a certain level of input voltage. I only have 10 volts going in, so I really can't have it ramped up that fast. So weird things are going to happen if you have a DC component into your V in. So we generally want to get rid of it. The way to get rid of it is to add a high value resistor in parallel with that feedback capacitor. That's going to bleed down any DC voltage accumulation in my capacitor, and that'll keep everything kind of nice and centered. And so again, you may do that in the lab, depending on exactly what modifications were made there. So you may see that. So anytime you have noise in the signal, you're going to get some errors involved in your differentiation. So in terms of differentiation going the other way, differentiation slope of the line. If I have a nice perfect signal, I have just this nice slope, and so basically slope's increasing. So I have this increasing value of the slope for my differentiation. If I look at a noisy signal, so these things are kind of offset up and down a bit, my slope kind of jumps up and down kind of all over the place. So the actual value of the slope kind of goes up, goes down, goes up. And so you get this really messy differentiated signal. So even though the input signal is only slightly noisy, the output signal is actually very noisy. So you can have some significant error in there. Again, we have some differentiator op-amp circuit that we've seen before. And we found the output voltage in terms of the input voltage, again, based on this RC values for the circuit. And again, here, if I have some input voltage, nice triangular wave, I get the square wave out. So positive slope, some constant value gives me a constant value for the out, same thing for negative, constant value down there. This has actually been inverted, so this should actually be upside down based on this drawing, but drawing right side up. And so lastly, we also multiply and divide signals. So we saw, came back in week 5, we saw summing op amps, so you can add signals together. We found we can integrate, we can differentiate. We also multiply and divide. We do that by adding and subtracting logarithms. So if you remember your log rules, if you add 2 logarithms together, that's the same as multiplying the 2 things inside the logarithm. So if we have a way of converting a signal into its logarithmic form, we can then multiply and divide them by using those summing amplifiers. And so to convert a signal into its logarithmic form, you can take an inverting op amp, very simple circuit, but replace the feedback resistor with a diode, cathode connected to the output. And then for diodes, we have the diode equation that the current is I0 e to the QV over KT minus 1. Generally call that V over V star. And then V stars, those constants. And then usually V over V star is fairly large. So if that's fairly large, this first term is much bigger than 1. So don't really need to worry about subtracting 1 out of it. Just get rid of that minus 1. So my current through the diode is I0 e to the V over V star. And then kind of standard method again, if we use op amp rules, and so rule 4, negative feedback, V minus and V plus are the same thing. No current going in from rule 3, the minus or plus inputs. Take the junction rule at that point. You'll find that V out is related to V in using the natural log. So again, I've converted this into natural log form essentially. Because it's minus, if I add this to another one, it's going to give me subtraction. If you want the addition, you can use an inverter. If you want to add signals, or in that case, I guess multiply signals, because addition of the logarithms is like multiplication. So with a minus sign, I'm essentially dividing signals. And then, of course, if you convert things into logarithmic form, add them, subtract them to multiply or divide, we're going to need to convert that back into exponential form to get the actual value. And so we need an op amp to do that as well. And to do that, we basically switch the positions of the resistor and the diode in the previous circuit. So this op amp here will convert my logarithmic form back into normal form, or in other words, I'll take the exponential of whatever I'm feeding it. So as I said, if I'm feeding it a logarithm, it's going to give me back that initial form. Again, using the same rules and same procedure, you can find the V out for this guy is related to the exponential. So that's why it converts to exponential form. Again, minus sign here, want it to be positive, use the inverter to do that. And then last thing to mention, we've seen all sorts of op amps, all sorts of configurations. We now know how to add things, how to subtract things, multiply, divide, take logarithms, exponentials. So we can do a lot of things. We can essentially make an analog computer out of all of these op amps and have them perform mathematical calculations in the analog domain. Solve differential equations of any order, even the non-linear ones, again by using those integrations and differentiations that we can do. The problem with that is that all that is done with analog signals. Computers are generally digital devices, and so using digital signals into computers is a much more efficient way to use computers. That's what they're based off of. Problem with an analog computer is that each problem is going to need its own unique circuit. So you need to solve something by multiplying and adding, then taking a logarithm. You have to build a circuit that does those 3 things in that order. So that's kind of the downside. Upside is that there's circumstances where these analog computers can be more accurate and less noisy than a digital computer. And another advantage is that the analog computer is configured to be an exact analog of some physical system that you're trying to model. So some mechanical system undergoing vibrations, you can model that with these analog computers. If you want to see detailed discussions of that, there's some websites here, examples of those, if you want to go through those and see them. So that is the end of this week. Hope you enjoy the labs, and I will see you in class.